So that might be a rude awakening.
You can start looking at these seminars.
Yeah.
I was looking at the board, like I'm interested in data science and there's a data science one on the 27th.
Okay.
Interested in that.
Good. Yeah, you guys should embrace the university, right? I mean,
You don't get interesting seminars like that in the computer science department. You just get people saying we want to hire you and calling it a day.
yeah, well, arts and sciences is good for some things. Like, and I would say, there was a period where I wasn't in academia, and it's a lot of fun to be able to kind of like think about things. And there's not a lot of space for that in the world. So, you should really try to enjoy it when you're here, or, make a career out of it. Really like it. Okay, so I know,
We got Zoom here.
yeah, I've got someone on Zoom. I'm a little worried.
I hope they'll go in there and see if there's other people.
We'll see. And hopefully people will wander around and find us. We'll see. We'll see. Or they won't, right? Okay. Okay. So let me get to our class. And we're problem session 4. All right, so I have no idea. Noah, I don't know if you, Timothy, Noah, you should feel free to unmute yourself. I think we'll be able to hear you. Maybe one of you say something to see if I can hear you.
I'm here. Can you hear me?
In the ether.
A little bit.
A little bit.
Turn you
Okay.
up, though. Where's it coming from? Okay, I'm gonna try to turn you up. You say it again, Timothy? Tim?
Can you hear me now?
Yeah, I can hear you, just a little bit.
Okay. You probably can't hear me that well because I'm listening to this while driving.
Okay, a little quiet. So here, I'm gonna. Let's see. 100%. Well, I can hear you, but what might be better is if I chat.
Chat is right in the middle.
What might be better is if you write a question in chat so that I can see it. Because I'm not really 100% on hearing you. You have to be real quiet. So let's start. Okay, you can probably can't hear me well because, okay, you're listening through Bluetooth. That's true. I can't hear you well. I don't know if it's because of Bluetooth. But why don't we go to one of you two? You guys can put in the chat one of the questions you'd like to see discussed, if you have one. Write it in the chat. Okay, or not, maybe, okay, so,
Of course.
I have,
of course, okay. Let's go to,
I was 5'6" and 8.
5'6".
And 8'8". I think 8'8" is probably it.
It needs a funky one. I feel like I can talk through it,
Yeah,
but not well.
I can't really formalize it. And 5'6", I think I'm just not thinking about it right.
All right, 5'6". Okay. Yeah, that's, so they gave a very nice hint, actually. So let's see. So oops, sorry, guys. A little slow. Let's try this again. Let's take 5'6". All right. All right, so here's 5'6". Asking for the center, and I actually didn't define in lecture the center. Of course, it's in the book. So let's take a look. So the center, so if you have an arbitrary group G, its center, which is usually denoted ZG or Z, it's a subgroup of all elements. I'll write it down like this. It's all elements H and G that commute with everything, commute with all of the other elements. So such that GH equals HG for every G and G. Okay, so that's the definition of the center, and this question is asking about this for matrices. So
The identity be a center?
identity will always be in the center.
This
So
has to be part of the subgroup, right?
yeah, so you can show that this is a subgroup, that the center is a subgroup, and one certainly commutes with everything because I multiply on the left or right, I get back that thing. So yeah, so one is in here and it is a subgroup, so a non-empty, it's a subgroup. So now we're looking at GLN. So let's let A be and we'll give ourselves entries of A be an element of the center of GLNR. And this hint is really helpful because I think without the hint, you're going to struggle to sort of get this sort of general. I mean, it's going to be too much information in a sense. So it's just test it against elementary matrices. Test it against elementary matrices. And I guess you can well, maybe the best thing to do, actually, now that I think about it, would be to test it against the third, I forget the type, what type, so I think this, what was the first type? The first type is switching, yes? And the second type was multiplying by a non-zero?
Yes.
Okay, so the second type seems to me a very reasonable thing to start with. Try the second type first. So let's take E to be the matrix. So 1 all along the diagonal until you get to the ith row column, and then you put a C in there, and everything else is 0. So this is the ith row. If you want, you can write this out. You can write it out using these standard basis matrices as follows. You can say it's the sum of EJ, EJJ, I guess is what we call them. J not equal to I plus C times EII. I mean, if you want to write a formula, but you know, it's fine just to stick with this one. Now let's take a look. So if A is in the center, what do we know? We know it commutes with this matrix. Here, of course, C is non-zero. So the only requirement here is C is not zero. So A commutes, and we'll assume also that C is not 1. I mean, we'll take E to be, we don't want, C equaling 1 is not going to be very interesting, as we know. That's fine. So let's look at E times A. What do we get? You guys can tell me. So we'll get A11. I'll write a little bit of it. A1N. A21. A2N. I'm assuming I is bigger than 1 and 2. What happens when I get to the ith row? Right. Once I get to the ith row, everything gets multiplied by C. And then everything else stays the same. So that's multiplying on the left by A. Now let's multiply on the right by A. So you should, if you're writing this out, you know, you should maybe include some words, right? Like I'm talking while I'm writing, so the words are there, but you know, for when I read it, it's better if I understand that you know what you're doing here.
Is part even necessary, or can we just say that we know the elementary matrices
Mute?
or not to, but they, you can multiply on either side, that would be the same. The EA is
Well. Okay, so what are we trying to do, Kale? What are we trying to do?
don't we know that?
We're trying to determine what A is. We want to know what A is. We don't know. We said it's in the center, but really we don't know what kind of matrix it is. I think that's the key thing here. So we want to know what kind of matrix we're dealing with here. And we don't. So what we're going to do is we're going to take some test matrices and say, well, if it's in the center, we know it has to commute, but we're going to see what we get. We multiply on the left and we multiply on the right. And then when we set these two things equal to each other, we're going to learn a little bit about A. Because we don't really know what A looks like. Because certainly not everything is in the center. In fact, we'll see not very much is in the center. So what happens if we multiply on the right by E? Well, someone can tell me. Will it?
No, because it does it. It does it different.
So we didn't talk about this, but in the class, but we did talk a lot about how row operations are. You can think of them as multiplying on the left by elementary matrices. If you multiply on the right instead, those become column operations. And so in fact, what happens here, and you can check this just by hand, is that what's going to happen is you're going to actually multiply the ith column by C. Oops, CN. CA sub n. And everything else stays the same. Now, for this to be in the center, for this matrix A to be in the center, these two have to be equal to each other. Okay, I'm glad you found it. So for A, for Since, well, I guess let's say since we already assumed it, A is in the center. We have, well, we can look at, well, I'll just write it this way, that A, let's look at Aij, C times Aij. That's the entry here somewhere. Well, if I look at that entry, and as long as I is not equal to j, so I'm off the diagonal, the entry here is C times Aij. The entry here is just going to be Aij. Or I not equal to j. So what does that mean about Aij? C is non-zero. And it's not equal to the identity. I mean, more importantly, it's not equal to the identity. It's not equal to 1. So what number can I multiply 3 by and get that number?
Or not
3 times, huh? What number can I multiply 3 by and get that number?
You what, 3?
Yeah, no, get the number that I started with. What number would what number for Aij satisfies this equation? What's the only number?
C?
C squared equals C?
No.
Is it 0?
0. Great.
But I thought we said it wasn't gonna be, oh, the entry is 0.
The entries are 0, C times.
Okay, now I'm following.
So if I is not equal to j, gosh darn it. If I is not equal to j, the entry of A is 0, which means A is a diagonal matrix. Okay, that's a big simplification, right? You start with a general matrix, you just went from like, n squared variables to n variables, right? So now we've got a diagonal matrix. Because, so sure, we chose a particular I, but I was arbitrary, right? I was arbitrary. So we know that much. But is that enough?
Okay, it is.
Well, let's see. We know some other elementary matrices. So let's look at, so now consider Eij. We'll just say E1I for I not equal to 1, right? And this is that elementary matrix that, if we think of it in terms of row operations, switches the ith and first columns. Switches those two rows. But if you think, I mean, as a matrix, it's just, you just take those rows and you switch them. Right? So it has everything along the ones. So then Eij, oops, E1j A. As I said, this is the operation that will just switch the first row with the jth, or with the ith row, pardon me. So we'll get zeros here, and then we'll get Aii here. Everything else is zeros. Here we have A22. We get 0 here, and we'll get A11 here. And Ai plus 1, ANN. So everything else is 0. So this is what we get multiplying on the left. The other hand, if we multiply on the right, again, this row operation now turns into a column operation. Turns into a column operation. So we get something that that looks exactly like this. Except we're switching the columns, which means this goes to A11. This is AII. Which means since these have to be equal, these numbers have to be equal. So A11 is equal to AII. I don't need a comma there. For every I. Yep. So thus, the center GL and R is precisely diagonal matrices that are just have the same value on the diagonal. So constants times identity. So to say A times this identity matrix, here A is non-zero. The center is actually just isomorphic to R times, right? Just the group of real numbers with multiplication. You multiply these. It turns out that, you know, if you consider, so you might think, well, there's this other subgroup, which is in some sense like orthogonal to this group. I mean, it's not, it's maybe complementary is the correct word. A special linear group, right? It's kind of in some sense complementary. It has a little bit of an intersection. And that group actually is this what's, well, I'm lying a little bit. So a minor modification of that group is simple, which means that it's sort of fundamental. And so GLN actually just has this trivial bit, which corresponds to its center, and then something that's very fundamental and simple. Matrices are very, they're one of the types of simple groups that kind of appear in the classification of finite of groups. So, anyway, ignore that. What was the other? What was the other?
The one where it has to be ordered of 25, and then you have to prove that there at least one is 5, and if only one of them is 5, then it's
I don't. That's
all
like,
that funky stuff.
what was the name? What was 8.8?
No, yeah, 8.8.
8.8. All right, so please do, you know, these are, this isn't meant to be like, please write down what I'm doing. It's more meant to be like, you know, use what I'm doing and write out your own argument, you know, if, and, you know, with some help here. So please do write a little bit more than what I'm writing. Or at least, you know, clarify what I'm doing, because I'm not really preparing this. I'm just kind of trying to, when I looked at these problems, these looked good to me, but, you know. All right, so it says let G be a group of order 25, prove that G has at least one subgroup of order 5, and that if it contains only one subgroup of order 5, then it is a cyclic group. Okay. Good question. So this is from section 8.8, what is, I'm trying to think of what, is that the chapter, or is that the section on? It's on cosets, okay. Okay, so, well, one thing you can add, I mean, one thing you, so, okay. All right, so help me out, guys. Like, tell me what you think here. And based on, maybe think about today's lecture.
Well, I know 5 is probably going to be part of it due to something with Lagrange's theorem, because everything has to be divisible, and prime numbers are, since it's a cyclic group, if it is prime.
Wait, what?
We're gonna leave that out.
Wait, what did you say? So,
Something about prime, then if it's cyclic, then if you have like a power of a prime as the order, then you have to have like every other part of it, like 5, 1, and 5 squared as possible parts.
so so first of all, don't assume more than you should. Okay. So like if you're at a place, if you're asked a question like this, you can't assume, for example, I mean, it's asking actually, whether or not the group G is cyclic. So you shouldn't necessarily, you certainly shouldn't assume this is a cyclic group, right? It may not be. So, but you did say the word cyclic. And so in lecture today, it came up a couple of times. How do you look? I mean, it's asking you to find a subgroup of this group. So what is the I don't want to use the word prime. What's the main way the only way right now that we've talked about in class to find subgroups of a group?
To make it a cyclic group.
Choose an element. Choose an element and look at the cyclic group generated by that single element. That's how we do it. I mean, this is really the first way to start talking about groups, is you just say, okay, well, let's take an element and see what you get with that one element. Don't think of the other things. Just say, okay, start with that one element and see what you get. If that element's the identity, you just get the identity, right? But if it's not the identity, you will get a subgroup. You will get a subgroup. It could be the whole thing, or it could be a proper subgroup. But those are the two options. So I would take that in that order, or in one of those orders. I mean, I would say, okay, so let's start by choosing an element A of G with, I don't want the identity. The identity doesn't give me anything. And then I can define, I can look at it's the cyclic group generated by that single element. So consider A equaling A, which is a subgroup. This is the notation for the cyclic group generated by this one element. It is a subgroup. Now, you had mentioned Lagrange's theorem. What do we know about this cyclic subgroup? It doesn't have one element because A is not the identity.
The subgroup has to divide the regular.
Subgroup?
The order has to divide, I mean the order.
That's okay.
I should
It's
be
all
more
right.
specific.
It's all right. It's okay. We're all learning this language. I mean, it's okay, you know. All right, so, except me, I know. So by Lagrange's theorem, one of two things happens. Well, by Lagrange's theorem, the order of this guy divides, oops, let me not use jargon, divides the order of G, which is 25 by assumption. So since A is not equal to 1, the order of this guy is one of two things. What are they? What is either
25.
Or 5.
either 25 or 5. Okay. So let's take the first case first. Why not? If this is 25, then, well, this is equal to G, right? So G is cyclic. And can you find, so now that if in the case where this is cyclic, now you're in this situation you're talking about maybe, right? Where you have a cyclic group. And now you can ask, okay, what are the order 5 subgroups of this cyclic group of order 25? I'm going to say the only, or maybe the unique, cyclic or order 5 subgroup. But someone tells me tell me what it is. Well, I'll start you off. We can start. It's one, it has identity. When I write one, I mean the identity. I don't mean a number. I mean the identity.
Is it
Well, what do you,
the
what's in it?
powers of A?
It's got 4 more elements.
Five, maybe?
I thought an element.
You're close when you say, so, guys, these groups, they're not numbers.
Oh, yeah.
Remember, they're like butterflies or, pancakes. I don't know. They're something abstract, but we do know A is in that set.
A inverse.
A inverse is, well, not in this set. We know A is in G. But A does not have order 5. Well, if you look at, so if I have a subgroup and it contains an element, it contains this, the cyclic group generated by it. So it doesn't contain A because I'm saying this is order 5. If it contained A, it would have order 25, would be the whole group.
Your subgroup that doesn't need to have the inverse of whatever.
Oh, it has inverses. Subgroups always have inverses. But it doesn't have the inverse of A. What elements could it have?
It's the first.
A to the 0 is 1.
And it's just A squared, A squared.
As A squared, think about A squared. If it has A squared, it'll have A to the 4th, A to the 6th, A to the 8th, A to the 10th. It has too many elements. Has too many elements. I know this guy only has 5 elements. One. The powers of A. Which powers of A, Tim? What? 5, 10? Right. A to the 5th. A to the 10th. A to the 15th. A to the 20. That actually is a subgroup. If I take a composition of any of those two, I will get something within that group. The inverse of A to the 5th is A to the 20th. If I multiply them together, I get A to the 25th, which is 1, because that's the order of A.
Why isn't A to the 25th in there?
A to the, because it's 1, because it's the identity.
Yeah, wouldn't it be the identity?
Oh,
It's a cyclic group, it has finite order. This, and you can, okay, so this is not, you need to show, so I'm gonna, this gets you started, show why there aren't any others. And the point is if you, I mean, I'll say verbally, if you chose something A to some other exponent that wasn't, multiple of 5, you can see that you get everything. That follows from this theorem about the relative primeness of things. Because it's not a multiple of 5, that means it's relatively prime to 5. So in fact, you can get that number times something plus some other number times 5 is equal to 1. That'll give you a way of actually getting A from that, whatever that is. You can do it that way. Should I say something more about that?
it's a little.
Okay, so let me give an argument. So suppose H is order 5 subgroup. And well, we know it's this, it's contained in G. And A, let's say to the I don't like that I'm using A now. A to the, I'll call it that's a good letter. K. A to the K. It's not a very good letter, but okay. A to the K, A to the K is in H, where 5 does not divide. Not divide K. Of course, K and K is in this list. Well, this doesn't matter so much. I don't really need this. I'll just say that. So 5 is prime. K, so that means it's relatively prime to K. So 5, GCD of 5 and K equals 1. And by this theorem we had, there exists, there are numbers, there are integers R and S, so that a to the, oops, 5R. I'm sorry, I shouldn't say 5. Maybe I'll say 25. I mean, this is certainly true too. So let me go 25. I think 25 is easier. 25R plus S times K is equal to 1. Right? This is just that. Maybe I should put the R in front of 25. Right. This is that theorem we had. If we have relatively prime things, there's some combination of them that gives you 1, or whatever the, or if you have a greatest common divisor. Okay, so thus, a to the S to K is equal to a to the 1 minus R times 25. This is equal to a times a to the R times 25. I mean, this is maybe inverse, sorry. Inverse of R times 25. A inverse to the R times 25. This is equal to a times a to the 25th power inverse of R. You take the a inverse, if you want, you take a inverse. But a to the 25th is 1. It's an order 25 element. This is equal to a. What that says is that if a to, so this is also a to the k, sorry, this is a to the k to the s. That's not 5. So you're saying if a to the k is in that group, then its power to the, its s power is a itself. But then it has all the elements of G. So you can keep taking powers. So that's not order 5. That's a contradiction. I don't know. Some people like writing this, I guess. It's okay too. Anyway, that's the argument. So now this is the first case. So what you see in the first case is either if it has order 25, the cyclic group, then there's a unique order 5 subgroup. Now suppose it has, now suppose A has order 5. Then we can say, okay, if A has order 5, then we found an order 5 subgroup.
Move the order signs around the general.
Oops, yep, thank you. So the question asks to find one, we found one, and you just need to wrap it up with one more statement, which is that if it's not cyclic, then we can find another. So assume G is not cyclic. Okay, so what do you think? How do you think you could find another one?
Find another subgroup of order 5.
How are you going to do it? You need to find one more to be done.
Would you be able to say another element from G?
Okay, which element do you think? Should I take a squared?
A to the 5th.
Well, a to the 5th is 1, because
Yeah.
A is the cyclic group generated by A is of order 5. What should I just? I agree with you. What element should I take? Should I So choose, you guys tell me. I just need a little specificity, not a lot, a little specificity of where I should choose this other element. So how many elements does G have? How many elements does the cyclic group have? So,
It has to be, well, if you're dividing,
okay, that's true.
you got like 25, and if you divide it by 5,
So I'm gonna set of 25 things. I'm gonna set a subset of 5 things. Does the subset have everything in it?
well, if you have another subset 5, when you multiply them, the least common multiple needs to be the order of the group.
That's not always true. I mean, if I'm understanding what you're saying, which I'm not sure, but I think that there are some cases where what you're saying actually is true, but it's not for groups. If I take an order M group and an order N group, subgroup of a larger group, and then I take sort of the group generated by both, it could be a lot of things. It doesn't have to be any. It could be infinite. So I'm just asking, so I said, I don't want to take A, right? I don't want to pick the identity. I don't want to take A squared. Right? I want to take A cubed. So I've got a group, right? I've got a group. Let's just put this aside. This is my G. This is big world, 25 things. I know I've got 1G, A squared, A cubed, A to the 4th, and it's a cyclic 5 group, order 5 group. So these are all the elements in this subgroup. Is there anything else? Does 5 equal 25?
There has to be.
There are other
A
things.
to the 6th, A to the.
Whoa, no, A to the 5th goes to 1. And then A to the 6th is A, and A to the 7th is 2. So if I keep on multiplying by A, I keep on going around in circles. So that's the word cyclic group. It kind of keeps on going around. So that's all there is for A. But so are there other elements of G?
Yes.
You're supposed to say yes.
Yes.
There are other elements of G. If I pick anything from this set and take your subgroup, I'm gonna get that subgroup. Unless I pick one, I'll look at 1. So I don't want to pick anything from these elements. I just want to pick anything else. Anything else. So choose any B, which is in G, but B not in A, which we can do because there are enough elements. So tell me about. So then what about the cyclic group generated by B? So B is over here. And I look at the cyclic group generated by B. What about it?
Wouldn't it also have to be 5? Because if it was 25, then it would be the whole group.
Very good. If B is of order 25, it's either of order 5 or 25. If it's of order 25, I've just found that I've got a cyclic group, but I said it's not cyclic. I said G is not cyclic. So I'll just write that, it's 5, by that argument.
Would that also be a contradiction because you said that B was not in A? Or
No, it's not a contradiction.
it wouldn't be?
It's not. I'll give you an example. Since G is not cyclic. Let me give you an example.
I was meaning if the order of B was 25.
No, that would be okay too, because we could have taken, so if in this in the example we saw above, we could have let A to the 5th be our original A. And then taken B to be by which I mean, you could let this be this, here we have an order 5 subgroup. And if we took any other element in G of the cyclic group, we would get an intersection there. be order 25. But there are groups like this, and the example would be just take a cyclic group. So we know. So we didn't talk much about it today, but we do have this notion of Z mod 5. Where you can just do modular arithmetic addition on Z mod 5. 1 + 1 is 2, 1 + 3 is 4, but then 1 + 4 is 0. Because at mod 5 it's 0. This is a group. It's something we'll learn about a little more on Monday, but we can take Z mod 5 twice and consider pairs of integers. Mod 5. Well, this is the product group. So this is just two, it's all the tuples where A and B are both in, and then you just add coordinate wise. And this is a group. It is not cyclic. Every element that's non-zero has order 5. It's not cyclic. So there are many examples. I mean, this is actually the only other example of an order 25 group up to isomorphism. But you can start, there's more to say. So if you get larger, you get more, even richer examples and stuff. Okay. How are we feeling? How am I doing? Yeah, I've got a little. So any other questions?
Does that only cover the first half of the whole question? That's the.
Oh, I don't know.
Part of the question.
So yeah, let's look. So it said, prove that G has at least one subgroup of order 5. So we broke it down into 2 cases. In each case, we got at least one subgroup of order 5. And that if it contains only one subgroup of order 5, then it is a cyclic group. We showed that if it is a cyclic group, then it contains only one subgroup of order 5. And if it is not the cyclic group, then it has more subgroups of order 5. And so that gives us that second.
Oh, so it's related to that second case.
Yeah.
Okay.
Yeah, the first part we kind of dispense with, say, okay, well, we got it. Were there other questions?
Can we talk about 6.10?
We can. Oh, these are lovely. It's a good question. Great. Love it. Very different kinds of, very different questions. Okay. So a cyclic group of order 10, let's give ourselves a generator. So there are different notations. Sometimes you'll see C10 in some books. This refers to the cyclic group of order 10, but so I'll write it that way this time. And I'll use that generator. I'm just going to call it 1 for the identity, A squared. This is the theorem that we have about cyclic groups, that we can write all the powers and it'll stop at whatever the order is -1. And then it will just cycle around. Now, this is actually something I have a hard time convincing graduate students to believe. I don't know if I have a hard time convincing them to believe it. They have a hard time remembering. But it's like used a million times. Like it's always used. Which is, if I have a homomorphism from C10 to any other group, I want to know what that homomorphism is. The only thing I need to know is where that generator A is sent. I know where A goes, because it's a homomorphism, I know that A squared will go to the square of that place that it goes. A cubed will go to the cube of where it goes. So I know where everything in the cyclic group generated by A goes. So the whole homomorphism is determined by where the generator A goes. So if I want to classify automorphisms, I'm going to look at homomorphisms from C10 to C10, and I'm going to ask, where can I send A? So the question is, let's say we have a phi, we want it to be an automorphism, not just a homomorphism. So we'll say, suppose phi of A is equal to A to the R. Okay. Phi is complete, as I was just saying, phi is completely determined by R. It's completely determined by R. Right? Because if we chose another R, we know where A squared goes to A2R, right? A to the whatever, T goes to ART. So we know phi is completely determined by this number R. And we know that R is between 0 and 9. Because this is the full list of everything in this group. So maybe one of you can tell me a little bit about R. So here I'm supposing this, but I also want phi is an automorphism. Remember, that means it's an isomorphism. So I'll just say that. What can you tell me about R? Can R be 2?
Yes,
Okay, why?
because you said it has to be between 0 and 9.
I said it has to be, but it may have other things that it has to satisfy. So it can't be, yeah, I mean, it has to be between those numbers because this is the full list. What? How does that work? I thought I took this, thought I was not to be interrupted. My iPad is rebelling against my wishes. It's a local number though. Don't worry about it. Give me 1 second, guys. Just make sure my kids are okay. Think about it. Tell me what R can be. What can R be? Can R be 2? You said yes. I say no. I say yes if it were a homomorphism. I say no if I want it to be an isomorphism. Why do I say no? Am I just being belligerent?
Assume that A2, the A squared is not doesn't satisfy bijection.
Why? Okay, why?
It's non-invertible.
That's true too. As a homomorphism, there's no inverse. Why?
A squared to the 5th, that would bring you back to the
Good. A squared to the 5th is the identity. So if, let's just check it. If phi of A equals A squared, then phi of A to the 5th, as you just mentioned, is A to the squared to the 5th, which is A to the 10th, which is equal to the identity, which means A to the 5th, which is not equal to the identity, is in the kernel of phi. We have a theorem or lemma or something that says that a homomorphism is 1-to-1 if and only if its kernel is trivial, is the identity. This would say the kernel is not trivial. So it's not 1-to-1, and therefore it is not an isomorphism. That's right. It can only be between 0 and 9 in order to be a homomorphism, because because this is the full list of elements essentially. You could say it could be 11, but the point is 11 is the same as a to the first. So I'm just saying, let's restrict ourselves to a finite list of possibilities. But yeah, so this is that argument. So it cannot be 2. So certainly R can be 1, right? R can be 1 because that's identity. Since A to A squared goes to A squared, so on and so forth. It cannot be 2. Let's make our list. It cannot be, sorry. Here, tell already. Actually, let me start with 0. Can't be 0, but 0A goes to 1. So A is in the kernel. So what else can't it be? Same arguments. Can't be 4, because again, if it were 4, then if I took it to the 5th power, that would go A to the 20th, which is A10 squared, which is identity squared. That would be something in the kernel.
5, 6, or 8.
It cannot be 5 because then A squared would go to A to the 10th. It can't be A6 for the same reason. It can't be 8. So it has to be one of these 4 numbers. And you can show, because 3, 7, 9 are all relatively prime to 10, that these are indeed, that these will give you isomorphisms. Basically, the argument I gave a couple of, the last question is the same. You use this Bezoos theorem so that you can get back A by an appropriate power of A cubed or A to the 7th. So these will do. In fact, there are 4. There are 4 automorphisms of this cyclic group. All right. For the symmetric group, well, for the symmetric group, I want to say, pull this over and take a fairly good look at it. Oops, I just did. And I'll give you guys a hint, but I'm not going to go through all the details of this. So if you have an isomorphism and you have from a group to itself, say, and you have an element of order D, where does that element have what? And I map it to some other element. What does the other element have to have? What order does the other element have to have? Great, a D, the same order. Because if it has a smaller order, then we have something in the kernel. So, and it can't have a larger order because 1 goes to 1. So that tells me that if I have an automorphism of this group, since these are the elements of order 2, they have to get mapped to each other. I can't send order 2 element to an order 3 element. So that means that whatever kind of group of automorphisms I have, it has to sort of permute these 3 transpositions. I claim that you can arrange it so you can permute those 3 in any way you want. So in fact, the set of automorphisms of S3 is the same as S3. It's isomorphic to S3. Now there is, and so I claim that, and there is a natural way you can look at a homomorphism from S3 to the automorphisms of S3. And we take G and send it to conjugation by G. This homomorphism is actually an isomorphism. So you'd have to kind of work that out, but that's a big hint. to tell you how to do it. All right. Okay, guys. Thanks for joining the problem session online and in person. That was a ton of fun. I hope it helps.